we go. We are not going to probably get through all the examples today. That's not my goal. My goal is to get through a few of them and make sure we understand the guidelines so that you're at least ready to practice some of the more simple ones, and then we can practice again tomorrow and practice them more tomorrow. We're not going to have any new notes tonight or tomorrow even, because this standard always takes a few days to make sure that we get enough practice, because there's not really any whiteboard stuff that we can do with this. It's kind of just sitting down and doing the problems and working through them, how you get used to them. So, all right. This standard has to do with related rates. There's many real-life situations where one quantity is affected by two or more different variables, such as if you throw a ball through the air, what are some of the things that are acting on it? Gravity. What else? Resistance, friction, energy, the weight of the object. There's lots of different things that are acting on it. So maybe you're looking at wind speed. Maybe you're looking at wind speed as one variable that's affecting it, and how fast it's going when it's let go. That's another variable that's affecting it. So there are more than that, but there's at least two or more variables that are affecting something usually in a real-life situation. So rate of change is a topic that we keep discussing for good reason. It's one of the main applications of calculus, and it's one of the most useful because finding the instantaneous change of something is something that's used in several different types of fields. So even though this is like the kind of foundation stuff that you learn, the application of it comes later in lots of different ways too. All right, so we're going to talk about a general example of what a related rates problem might look like. So Michelle has a pretty box that she's decided she uses a water tank. Water problems like water tanks and filling things or emptying something is a very it's a very common problem that this is used for. So the water flows in at a certain rate. Let's say it's flowing in at 0.1 feet per minute. What are two things, and there might be more than just two, but what are two things or quantities that are changing as the water flows in? Water level, water pressure. What are some other things? The box is either closed or it's open at the top and the water's just coming in. So water level is rising. Air in the box is decreasing. What did you say, Zach? Oh, air is decreasing. Good. The weight of the water? Just like of the whole thing. Of the whole thing is increasing. What about if I dumped the water out? Would there be more water coming out of the box? So what's that called? The amount of water. The volume or the gross amount. Good. Okay, so there are many things that are changing as water flows in, but the two we're going to focus on, or what these kind of problems usually focus on, are volume and height. Or that would be the same thing like Sophie said, which is the water level, just the height of the water. You didn't? Oh, I thought it came from over there. Okay. Sorry. All right. Are these going to change at the same rate? Maybe, but are they going to change maybe at different rates probably? Like something's increasing a lot quicker than the other or vice versa? Okay, so this is going to be, no, it could be the same rate, but almost always it's not. They're going to be changing at different rates. So all three rates of change are related to one thing. A variable. An independent variable that nothing has control over. Time. An actual something, yeah. Time is something that all three are related to. Volume can't change unless time is ticking. Water can't flow unless time is ticking. And height can't change unless time is ticking. So that's why we have related rates equations, because it allows us to find those differing rates of change depending on what quantity we're looking at, and it's all in terms of time. Because time is independent of anything, and everything relates to time in these problems. So that can be our baseline that we compare stuff to. There are some guidelines that you can follow to make the problems a little easier. And I will say that some of this stuff, it's pretty essential that you do, like step 3 you have to do before step 4. Do you have to label your steps? No. But initially it might make it easier to label your steps so that you know you're covering your bases of everything you have to do. In related rates equations, they do have to give you some stuff that you know. So in the problem, it'll give you maybe a rate of change of something. So that's something that you know, you can write down. It'll also indicate what you want to find. So that's something I usually write right at the beginning. I write no, I know this stuff. Find, I want to find this. And it directs you the rest of the way. A lot of times, you're able to draw a figure. Sometimes they give it to you, but sometimes you have to draw it. And this is the important part, and I tried to indicate here, but if you highlight it or underline it or something, label any quantities that don't change over time. So something that doesn't change over time, you want to label with constants, meaning an actual number. And we'll look at problems like that today where it has constants. Any quantities that do change over time, what do you want to label it with? Probably variables, yep. So stuff that doesn't change over time, label with constants. Stuff that does change over time, label with variables. Write an equation that shows the relationship between the variables from step 2. So the picture is pretty important because usually the picture tells you what equation to use. Now, I'm going to have you make a list underneath of common equations that are used so that you kind of have a list to go off of for certain problems. One of the very common ones that you use is the Pythagorean theorem. Anytime it talks about something that has to do with volume, the volume equation of the object that you're looking at is the one that you usually use. So I'm just going to write volume equations, but the volume equation you use would depend on the object that you're looking at. So volume equations. We'll cover the most common ones. I will say the common ones like rectangle, circle, those ones you have to know. But if they give you a weird shape, they'll give you the equation. So volume equation, surface area, area. In general, the area of something. If area is what's changing, then the area equation would be what you use. And we'll add to this list as we go. There are a few others, but we'll come back to them. These are most common ones. All right, the fourth step you differentiate. Now, you take the derivative because you're looking for a rate of change. Normally, that's what you want to find. I want to say, find how fast this is going at a particular time. Well, that's the rate of change, so at some point you have to take the derivative. And we say with respect to time t. What this means is the same thing it meant when we did implicit differentiation. It means if your variable is not t, then you have to include a dx over dt or dy over dt or something like that. So if the variable is not time, then include dx over dt, dy over dt, etc. It just depends on what your variable is. So if we had r, it'd be dr over dt. And that's because all of the rates that you're looking at are in terms of time. So it'll say it's moving this fast per minute or this fast per hour. And so everything's going to be over dt. Why would we not need to include it if your variable is time? Because then what would this be? It'd be dt over dt, which is just 1, right? So that's why we would need to include it in there. And then the last step is to plug in plug in specific information to find what you need. So it'll say something like, find the rate of change when x is 2, or when time is 4, or something like that. That's the specific information that you would need. Okay, we're going to be doing this, and I'll be labeling steps so that you can kind of match them up later. You don't have to label steps in the problems that you do, but this will at least keep your notes organized. Okay, for example 1. Alright, an airplane is flying 600 miles an hour on a horizontal path that will take it directly over an observer. The airplane is 7 miles high. We're supposed to write an equation for the rate of change of the line of sight distance, and they give you the variable they want you to use. In miles between the observer and the airplane, how fast is z changing when x is 10 and when x is negative 5? When they ask you stuff like this part here, when x is 10 and x is negative 5, that's your specific information. You don't plug that in until the very, very end. So maybe mark that as your specific. And that's why it's usually written at the end of the question, because that's the final step that you do. That'd be step 5, yep. Our first step is to write down what we know and what we want to find. Now, what you know and what you want to find, these are going to be rates of change or variables or stuff like that. In this case, they give me a rate of change at the very beginning. In the first sentence, actually. What's the rate of change they give me? 600 miles an hour. Now, I have to assign that to a variable. And if you think, and we're going to draw a picture here in a minute, and actually it might be easier to kind of do steps 1 and 2 at the same time. We're looking at an airplane flying on a horizontal path. And we're going to assume that that horizontal path stays horizontal. It doesn't tell me that the airplane's going to decrease or go up or whatever. So it's just flying along this horizontal path. And so since this is a horizontal movement, usually horizontal movements we're going to label with an X. Like the x-axis is the horizontal axis. So I'm going to label that speed, since it's a rate of change, I'm going to label it as a rate of change. My x, or my horizontal path here, is changing at a rate of 600. The airplane is 7 miles high. This is something that I know as well, but it might just be useful for my picture when I draw that next. Because what I want to know, what I want to find, are usually just rates of change. So this is the rate of change I know. What's the rate of change I want to find?
How fast it's going at 10 miles. d over dt?
How fast? This is usually an indicator word.
7 miles.
How fast? But we're looking for a rate of change that I can write. So not dx over dt, but what's the variable I'm looking at changing? Z. So I'm looking to find dz over dt. So I want to see the rate of change, or how fast z is changing, that's what that means, when x equals 10 and x equals negative 5. You can write your specific information right there, but just keep in mind we're not plugging in specifics until the very last step. Okay, so that's what I know, what I want to find. Notice I didn't include any units. You can, you don't have to though, for this step. Okay, step 2, we're going to draw a picture. Now, I'm going to just give you the picture because actually for this question, the picture was given. But then we'll explain what this would look like. The plane, now you get to see my wonderful plane. That's my plane. Okay, your plane is flying in a horizontal path this way. The observer, I'm going to label, or actually I'm going to draw a little person here. The observer right there. And then we're going to label this picture with the things that are changing and with the things that are not changing. we're going to assume that the plane isn't increasing in altitude or decreasing in altitude. It's just going to stay on this horizontal path. And so the only side of this triangle that wouldn't change would be this side here. Its height above the ground. How high is it above the ground? 7. So I'm going to label that with a 7. As this plane flies towards the observer, is this length going to change? Yes. And since it's a horizontal length, that's my x. Is this length going to be the same thing as this length up here where the plane is flying?
No.
As this gets smaller, is this getting smaller? The same?
That's Z.
Yeah. Well, because we labeled up here that dx over dt is 600, right? That's how fast the plane is going. So it's this horizontal path. It's the same thing. We're just marking it along the ground, the horizontal path. That's fine. And then the line of sight distance is what they want me to label as z. So that's the line of sight means if the person was looking at the plane, the length of that segment. Okay, so you label what is not going to change. The height of the plane above the ground isn't going to change. But this side is going to change, and this side is going to change as the plane flies towards. Now, the other thing with this knowing this rate of change, this is actually going to be a negative 600. And this is a picture that would have been given to you in order to know that this has to be negative 600. Why does it have to be negative 600 here?
Moving to the left.
Yes, because the plane is flying towards the observer, and it's heading left, so it's a negative movement because it's going left. So that's a negative 600.
So is it showing direction?
It shows direction, yeah. Okay, so first step, write down what you know and you want to find. For this second step, I had us draw it, but that would have actually been given to you, so you wouldn't have had to draw the figure. Your third step is to figure out an equation that relates everything in your picture. Now, in your picture, you have a right triangle, and you have the three sides of the right triangle labeled. So Pythagorean theorem is the equation that brings all those things together, all three sides of a right triangle. So we actually start with the Pythagorean theorem. And I want you to label the Pythagorean theorem with what we have in the figure. So we have x squared plus 7 squared equals, equals z squared. And we can even simplify that to be x squared plus 49 equals z squared. All right, so that's our equation that relates to all three sides. And then the fourth step is to take the derivative, because we're looking for dz over dt, but we can't have dz over dt unless we actually take the derivative, because that's how you find rates of change. So I'm going to move left to right, take the derivative of each thing. So derivative of x squared is 2x, and because that's not a t, I have to include dx over dt. What's the derivative of 49? 0. And what's the derivative of z squared?
2z dz over dt.
Good. Okay. Now once you take the derivative, your derivatives are going to look like this, and then you will have stuff that you can plug in. For example, do I have stuff that I can plug in for x?
10 negative 5.
I have 10, or I have negative 5. Good. Do I have stuff that I can plug in for dx over dt?
600.
Yeah, negative 600. I'm looking for dz over dt, so what's the only other variable I don't have yet? Z. Now, when you have a missing variable like this, like I have stuff already up here I can plug in for x and for dx over dt. When I need something for z, you go back to your original equation. If I want to plug in 10 for x, can I find z?
You plug it in.
Yeah, if we plug it in up here. So here, we're going to have to do a little bit of side work here. Let me mark it down like this. To find z, use the original equation. And so in your fifth step, we're going to plug in information. Now, when x is 10, I'm going to plug in 10 for x. I plug in negative 600 for dx over dt because that was given to me in my first step there. I need something yet to plug in for z, and then dz over dt has to stay since that's what I'm trying to find. But to find what to plug in for z, I go back to my original equation and I plug in 10 for x to solve for z. So there I get 100 plus 49, so 149. And how do I find z when x is 10? Square root it, right? So I'm just going to write the square root of 149 in there and add that to what I find. So when x is 10, z is square root of 149. And I'm going to do something similar when I try to plug in negative 5. But let's go ahead and solve this one. You're going to have to just use your calculator, multiply everything on the left together since that's what's going on, and then divide it by whatever 2 times the square root of 149 is. So let me grab the calculator here. So it'll be 2 times 10 times negative 600. If you don't have a calculator, you should have already grabbed them. That's on the log. Okay. So you multiply everything on the right or in the left-hand side together, and then divide it by 2 times square root of 149. And you're going to end up getting a negative value here. So in this case, zz over dt gets you negative 491.539, round to 3 decimal places. And that has to have some units. What were my units?
Miles per hour.
Miles per hour. Now, does that make sense for this problem? If the plane is flying at negative 600 miles per hour, coming this way, would that change at a pretty high rate as well? Because what happens when you're looking at something in the distance? Does that, the distance changes between you, but what happens to your eyes? Like as it gets closer, what happens? You look up. And then as it gets really close, do your eyes move faster as you go up? Yeah. And then you would have to turn around and look at it, go that way. So the distance is going to, that rate or that line of sight distance is going to move slower and then move more quickly as you get closer. And vice versa. Yeah. It's 0.539. I just ran into my pothole of a. Did you say pothole? Yeah, pothole of my hole punch. Oh. Okay. So we get negative 491.539, and then we're going to do the same thing, and I'm going to have to turn over here, but do the same thing with negative 5. So instead of plugging in 10, we're going to plug in negative 5. I guess I'll do it up here. So 2 times negative 5 times negative 600 equals, 2. Now, is our z value going to change? Yep. So we come back here. If we plugged in negative 5 squared is 25. 25 plus 49 is 74. If I plugged in negative 5 here. 25 plus 49 is 74, so it would be the square root of 74. And then you punch it out just like you did before. And then divide it by 2 times square root of 74. You okay over there? Okay. Okay. There's just giggling going on, so I didn't know an airplane flying was funny. Okay, so dz over dt gets you positive 348.743. Now, why would this be positive and this be negative? What did you say? It's behind you now. Because as you're getting closer here, that distance is decreasing, right? And then, that distance is decreasing because the plane is getting closer. And then as soon as it passes over, what happens to the line of sight distance? If the plane keeps traveling this way and you stay put, it's this length, and then as it continues, if you keep watching it, that line of sight distance will get longer again. So because your line of sight distance would be increasing, that's why your rate of change is positive. And it's still miles per hour. Okay. So airplane problems almost always have to do with Pythagorean theorem because you have like a triangle that's made by all the measurements. It's a pretty typical one. Let's do example 3. So flip over to example 3. We'll come back to example 2. I tried to pick examples that have a different type of equation every time so you have at least one to match with whatever practice problem you're doing. So we have air is being pumped into a spherical balloon at a rate of 4.5 cubic feet per minute. Find the rate of change of the radius when radius is 2 feet. So we're going to do the same process. First step is to write down what we know and what we want to find. Now, this rate of change here, the units indicate what's changing. When something is being cubed in units, what does that usually refer to? Volume. So our volume is what's changing at 4.5 cubic feet per minute. So when you write down what you know, if the volume is changing, then label it dV over dt. If volume is changing, then label it dV. And we're going to make that a 4.5. And since it's being pumped in, then the volume of the air is going to be increasing, so it's going to be a positive value. Might be good to write yourself a note that when something's being cubed in a unit, that indicates volume. We want to find the rate of change of the radius. So how would we label that rate? That's what we want to find. What's a good variable for radius? R. So just label it dr over dt. And we want to look at it at the instant that the radius is what? When r equals 2. This, when radius is 2 feet, that's your specific information. So that doesn't happen until step 5. We don't do anything with that number 2 until the very last step. Okay. Now, this word spherical balloon, that's important here because a sphere is round. Usually a balloon has like a peak and then, yeah, it's a weird shape. So in order to use a volume formula, they have to tell you that it's spherical. Otherwise, you wouldn't be able to do that. An upside down pear. All right, so we're going to draw a sphere. As much as possible, try to make it look 3D. We're drawing a sphere. As much as possible, we'll try to make it look 3D. So this is behind the sphere. This is in front of the sphere. And I'm not the best at drawing shapes. I've gotten a little bit better, but my shapes are lacking. In your picture here, let's label what I know. There's not really anything I can label that isn't changing because isn't everything about a balloon changing when you're pumping it full of air? Like it's increasing, the volume's increasing, there's nothing that's going to say constant about it. So there's not a constant I can write here. The only thing that I'm going to draw in my picture then is this R value that is changing. That indicates. Okay, third step. Coming up with an equation that kind of relates to everything we're talking about. If they give you a volume rate, then use the volume equation. Okay? Don't make it too hard on yourself. It gives you a volume rate, use the volume equation, and we're going to be looking for the volume of a sphere. Now, the volume of the sphere, oh, you guys don't have your books. In your books, and this is just for future reference, like if you're practicing and need something that they don't give you. And I'll try to scan this in too, but in the very back, there's this like little grid. I'm sure you could look it up too, like what's the volume for a sphere. But the volume for a sphere is going to be 4/3, whoops, right there, 4/3 pi r cubed. So we're going to write that down. 4/3 pi r cubed. Well, we're just starting with the general formula. So third step is coming up with a formula that relates to everything. Since they gave me a volume rate, so we use the volume equation. Then your fourth step is to take the derivative. What's the derivative of v? Because we have to move left to right. What's the derivative of x? 1. So what's the derivative of v? 1 d v over dt. Right? Because we took the derivative of something that wasn't a time. Yeah. And then, is pi a variable or a number? It is a constant. So when you're using, or when you're taking the derivative of the right-hand side, you don't do the product rule. Please don't do the product rule. Because pi is just a number. So we're going to use the power rule here, just like we have before. I'm going to bring the 3 out front. When I bring the 3 out front, what happens to that fraction? It just becomes 4. So you get 4 pi r squared times what? I took the derivative of something that doesn't have a t in it. dr over dt. And then your fifth step is to plug in the specifics. So I'm looking for dr over dt. That's what I want to find. So that's going to stay dr over dt for now. Do I have something to plug in for dv over dt? 4.5. They gave me that. 4.5. 4 pi. Do I have specific for r? 2. And then dr over dt is what I'm trying to find. You should be able to plug in everything except what you're trying to find. And so then I'm going to take 4.5 and divide it by 4 pi, times 4, so 16 pi. So take this and divide it by everything over here. And we should get 0.0895. Now, what are the units for this? Feet per. Well, we're talking about radius. Radius is just the length, right? So it would just be feet per minute. It's not going to be feet cubed per minute. It's just going to be feet per minute. Now, this is a pretty small rate of change, but if you're thinking of a balloon, the most the radius increases is like the first few puffs when you blow into it, because it goes from nothing to something. And then after that, it just increases slowly every time you put a breath into it. Plus, this is feet per minute. This is over a minute, so it's not going to change very much over a minute necessarily. All right. Let's do, last one we're going to do together today, before I turn you loose on stuff. Let's do example 6, and then we're going to do the other ones tomorrow together. All right. We have another airplane problem. These are pretty common. That's why we talk about them. An airplane is flying on a flight path directly over the radar station and is 6 miles over the Earth. If S, and now I'm changing the very line, S is the line of sight distance. If it's decreasing at a rate of 400 miles per hour when S is 10, what is the speed of the plane? So let's start with writing what we know and what we want to find. Okay. So you look through, for the no part, you're looking for a rate of change. What's the rate of change they give you? 400 miles per hour. And that, it is decreasing. Good. So it's going to be negative 400. And that is attached to what variable? They give it to you there. S. If S is decreasing at a rate of 400 miles per hour. So we're going to say we know ds over dt is negative 400. Negative because you're decreasing. Now what we want to find is, they give me the specific information. When S is 10, what is the speed of the plane? Speed is rate of change. But we have to know what variable to attach it to. Looking back at this problem that we started with, this was our speed, right? How fast the plane was flying this way on a horizontal path. What variable did we use to indicate that? No, Z was the line of sight. X, right? When you're talking about like how fast a car is going, you're talking about how fast they're going on the ground. So we're going to label that as dx over dt. Okay. When S is 10, that's the specific information. And then this one, I did not give you pictures, so we're going to draw a picture here. But it's going to be very similar to any airplane picture that you have, which is like the one we did before. Airplane is flying in a flight path directly over the radar station and 6 miles over the Earth. So draw your airplane, which probably looks better than mine. Since your line of sight distance is decreasing, looks like what? Oh. Yeah, it looks more like a spinning top. Okay, this is going to be the radar station. This way, left. Because this has to decrease, which means it has to be going towards the object. This is changing, but the x here is the same thing as saying the speed of the plane, because the plane is moving in a horizontal path. And then what's the thing I can label with a number? There's something that isn't changing. 6, and it's 6 miles over the Earth. And then the other variable they give me is S, for the line of sight distance. Yes, sir. RS, radar station. Or you can draw a little person observing out of the radar station. Okay. So we have a triangle where we have all three sides. Pythagorean theorem is what we're going to use here. And we're going to label, or we're going to write the equation based off my picture here. So s squared is going to equal x squared plus 6 squared, or you can write x squared plus 6 squared equals x squared, doesn't matter. And I'm going to simplify that to be 36. And then in step 4, what do we do in step 4? We differentiate, because we're looking for a rate of change, so we can only find that when we take the derivative. Take the derivative left to right. So derivative of s squared is going to be 2s ds over dt. And then the derivative of x squared is 2x dx over dt. Good. And then the derivative of 36 is 0. So then we look at this problem, and we're going to plug in stuff that we know. I know that s is 10. I know that ds over dt is negative 400. I know that x is, I don't know what x is. Oh, sorry, this is step 5. Here. how do I find X? They don't give me X.
Plug it into the original.
Plug what?
The
What's the instant I'm looking for?
negative
When S is
10.
10. So you have to take that instant they give you, go back to your original equation and plug it in. So we're going to plug it in here. So it's going to be 100 minus 36, which is 64. What's the square root of 64? 8. So we're going to plug in 8. And so it might be good when you find that to put that under what you had. So like when S is 10, X is 8. Because you need both for your final step there. And then we're just multiplying stuff together. So 2 times 10 times negative 400, all divided by 16. And what are the units here? Miles per hour. And this is how fast the plane is going. Is that a logical answer for the speed of the plane? Yep. We'll get to that another day. Okay. F4 type for this is just something that would involve other calculations besides these straightforward ones. The 5 steps. All right. We're gonna start this now. There's several examples that I wanted you to do that are like the ones that we did today. So don't feel like you have to go in order of the problems in the A1 practice. Pick the ones that look similar to this, volume problems or triangle problems, plane problems, and try a few of those first before you tackle other ones. But we are going to look at the other ones tomorrow, the other 3 that we didn't do today, and look at it again. So I would pair up with somebody. It's good to talk through this book
Are we still
and
gonna
get started on the A1 practice.
Are we still gonna record that too?
Yes. Will you guys start this? All right, go ahead and split up if you need to or move around. It might be good for everybody to stand up, at least stretch.
Oh, you're
Get some oxygen to your